last lecture, I think I made a fourth step in deciding I would talk about two-dimensional Yang-Mills theory, because I wanted to have it on hand as an example, but I suspect I'm not actually going to have time in the remaining 3 lectures to do anything very much with it. But because I didn't say it very clearly, let me say what I should have said. We have a compactly grouped and I considered this algebra of C-infinity functions and a convolution. I already was somewhat wrong there, and what I meant to say was the invariant functions. We want to get invariant under conjugation, the plus functions. In other words, the center of the convolution algebra. That was the thing that I wanted to convey. So this is an algebra, and it has a linear form driven by evaluating the identity elements of the group. Now, of course, it's an algebra without a 1, so it can't be a Frobenius algebra in the ordinary sense, but it has a 1-parameter group on it, UT, which is the heat flow, and this is e to the minus, so that's the Laplace operator on the group. So this is the V group with a method and the algebra G. And of course this heat flow is just convolution with an element. So UTF is something silent T involved with F. But these things of silent T are an approximate unit. In other words, epsilon T is a function on the group, which tells you, if you started with a delta function at the identity element of time 0, and then it flow under this heat flow time t, then it will become, after time t, something like that, some Gaussian-looking thing, which is precisely epsilon t. And this heat flow is involved in that. Well, so I wanted to explain why this gives you a field theory defined on 2-dimensional manifolds with area. So I had to say essentially 3 things. We already explained that surfaces can be patched together out of 3 kinds of surfaces, which in this case is an area. So I have to tell you what those things do. Well, you see, this has to be an element of the algebra, and it will be precisely the thing E sub A, silent sub A. This is multiplication. This means multiplication in the algebra followed by A. And this is the composed with convolution. So those are the 3 things. Now, there are lots of beautiful things you can say about this theory. The most obvious thing is that if you take a closed surface of genus G, then you can say what the number which the theory associates with that is. So you think of that as a cobordism from the empty manifold to the empty manifold. Given by a beautiful formula, it's the sum over all the irreducible representations of G of the dimension of the representation to the power 2t minus 2, and above that, so this is of area A, in A there, where this is the Casimir eigenvalue of the representation G. Yeah, so this is an operator from C to C, so it is a number. Now, so Wick proved a beautiful theorem about this, which explains why it's called two-dimensional Yang-Mills. And if I have time, I'm going to come back and talk about this. But one of the very nice things is that, remember I told you what the Yang-Mills action was, the integral over the surface of the norm square of the curvature. Well, if you make the surface very small, you let A be very small, that Yang-Mills action becomes very big. If you think about it, it scales inversely with the square of the length. So, as A becomes small, we can ask what happens to this asymptotically. The measure should be concentrated on things of very small curvature. And the nice fact is that this becomes an integral over the moduli space of flat G bundles on M. Of a differential form, and there's some constant which I won't talk about. The following differential form, omega plus 1 over 2a c plus order a to infinity. So as a gets small, so what is this? This space of flat bundles is well known to be a symplectic manifold. You see, its tangent space at any flat connection is H1 of the surface with values in the Lie algebra. Like a cut product and the product of the algebra, that's symplectic vector space, symplectic manifold. This is its symplectic form. So this is a 2 form on the manifold, and this is a 4 form on the manifold, which is, you see, the inner product on the algebra gives you a quadratic, think of it as a quadratic function on the Lie algebra. That defines a 4-dimensional cohomology class for bundles with structural group G. If you restrict these flat bundles to have a family of them, restrict them to a point and take that characteristic class, that's C. So this is a 4 form on the moduli space, and this is a 2 form. So when you integrate this, you get a differential form with inverse powers of A. So this is a polynomial in 1 over A plus order infinity. And unfortunately, I messed this story up because if I tell it to you the way I just said it to you, this formula is slightly wrong, because this is got a singularity if I consider it the way I did. There's a singularity in this space of the flat bundle that makes a difference. So there's one additional term connected with that. And if I had more time, I would write down a formula which avoided that problem where we look at a different modification of the space bundle. But I don't want to go into that. So I'm going to try and talk about something else. And if I have time, I was hoping to explain why this formula is true. But I'm going to go on to do other things now. So, let's go back to the very general theory. I explained that there was this theorem that two-dimensional topological field theories correspond to commutative Frobenius algebras. And I said one can prove that, for example, by Morse theory, and there are lots of versions around. But it's perhaps interesting to consider the case of a one-dimensional Frobenius algebra. So this will correspond to a field theory, two-dimensional field theory, where for any one manifold, the dimension of this is always 1. Yes, this was the space associated with a single circle in tensor rather than together. So this is sometimes referred to as an invertible field theory. Because clearly field theories can be tensored, and clearly you can tensor with the dual of a theory, and that will be an inverse under tensor product. Well, in this case, you see, this means that A is necessarily A sub lambda, or some non-zero number, which is just a complex number where the linear form is x1 to some number lambda. And if we make it a unitary theory, that number will be on the unit circle. So I mainly think of unitary theories where this is on the unit circle, but that's strictly speaking math. Well, in this case, you see, it's absolutely trivial to know that this gives rise to a theory, because, you see, when we have a coordinate from n0 to n1, we want to know what the map from A to A is. Okay, because it's always the same. Well, it will, I think we use just a complex number. It will simply be multiplication by lambda and half the Euler number of n. That is certainly a field theory, you see, because any closed one manifold is a bunch of circles, so it has Euler number 0. The Euler number is just the homotopic number of points, so to speak. So the Euler number has the property that for the union of two things, the Euler number adds if you subtract the Euler number of the intersection. When we string together these coordinates, because this has Euler number 0, the Euler number adds, so that clearly is a theory. You may wonder what happens if we change the sign of changing the sign of the square root of lambda. That gives you an isomorphic theory. When the theory depends on lambda, but the isomorphism. Now, so that seems so trivial. One asks oneself, why can't one give a similar argument for the general Frobenius algebra? And you can, and I thought it's worth pointing that out because, again, I can explain, that leads me to something else I wanted to say. It's kind of a trivial remark. But so, suppose we have a general Frobenius algebra, it's a finite dimensional algebra. Well, we know that when we have a surface, we can cut it up into pieces and assign an operator to it associated with Frobenius algebra. What we have to prove is that the result doesn't depend on how we cut it up. Well, so supposing we have any algebra, we can deform it a tiny little bit, just as an algebra, to make it a semi-simple algebra. The semi-simple algebra is one which is, as an algebra, is just a direct sum of a finite number of things like that. Well, of course, if we deform the algebra just a tiny bit to make it semi-simple, then the theta which we had before, which was giving us an inner product, will still give us an inner product. It will stay non-degenerate for a sufficiently small deformation. So we can assume that we have our Frobenius algebra is just a sum of things like that. You see, because if we want to prove some identity for about two different ways of decomposing the surface, if it's true for all semi-simple ones, then it will be true for all of them by continuity. So that raises the question, as it was trivial to say what the field theory was when we had one-dimensional Frobenius algebra, what happens when we have one like this? In other words, what's the operation on theories which corresponds to taking the direct sum of copies of the space for a circle? Well, that's kind of trivial, and you can say it in a lot of different ways, but it's worth, I think, it leads me into this topic. So we're going to come back to that in a second. I'll digress and tell you the concept. I said that we wanted to consider not just theories defined on all Riemannian manifolds, but often we wanted to talk about theories defined on manifolds with some kind of additional structure. And because the obvious, I'll just say a few words about that. So the simplest, well, the most famous example, not the simplest example, is well, like gauge theories in general, and quantum electrodynamics is obviously historically and in every other way the prime example. So what is the situation there? Well, you see, we make these gauge theories in two stages. We are interested in Riemannian or Lorentzian manifolds, and now this can be in any dimension. So the space-time dimension doesn't make any difference for what I'm about to say. And we'll consider, first of all, a theory defined on Riemannian manifolds M, with a complex spinor bundle with a unitary connection. So, it's exactly equivalent to say Riemannian manifold equipped with a Dirac operator in the usual sense. Well, let's call the category of these structures B-GAN, that's such structures. It's a groupoid. I mean, the objects are these bundles and the connection and the morphism is just isomorphism of the bundles and connection. Well, so in the mythological picture, remember, which we had in quantum field theory, you see a gauge theory is a theory which comes where the space of notional fields is 6 over this M, if that's all right, B M over the isomorphism passes of such things. So I'll write E to the bundle. So in quantum dynamics, we have an E, which is an object of this, and the notional space of fields is a pair each side, where the side is just the cross-section. Smooth cross-section. Just to be clear, what does this space look like? If you have two spinor bundles, both have E and E prime, then automatically this is got any two of them differ by tensouring with a complex line bundle with a unitary connection. So this space is a principal homogeneous space for complex line bundles with connection. So this is what you ordinarily call electromagnetic fields. In this situation, what do we do? Well, first of all, you make the theory in two stages. We say that on the space of these manifolds, these pairs and these manifolds in structure, we have a theory defined. So there is a theory. I'm really only interested in this schematically. I'm not going to say anything non-trivial about it. This is a theory which, to a D minus 1 dimensional manifold in its bundle, gives us some vector space which I'll call F and G. And to a cobordism, where we have N or E or N1 E1, and some M with E on it. So it's a cobordism with bundles like this. To this, we would assign an operator. so my ends, the D minus one-dimensional manifolds are always closed compact manifolds, and these coordinates, of course, are compact manifolds with downward. And I'm not going to tell you how to make this free-Fermion theory, not at the moment, but let's suppose there is such a thing. So this is defined for manifolds equipped with a given electromagnetic field, then we can make a theory of this set. So I just want to leave that schematic for a moment. I don't want to tell you about the theory, I just want to say, let's just believe.
Where does it take values?
Sorry?
Where does it take values in? This theory, where does it come from?
Oh, so this is a topological vector space. So this will be some fermionic Fock space made from the sections of the spinor bubble. You see, we have this vector, for a given E, we have a vector space of sections, and we make some semi-infinite Fock space out of that. But it doesn't matter for the moment, because I just want it to be a theory defined on this larger category.
More than general topological, I think, again, locally. Convex?
Correct?
Should it be?
Vector convector, absolutely. But don't mind, it should in this case definitely be a Hilbert space. But this is just meant to be schematic. Really, I'm not going to say anything about it. I just want to explain the formula that there is such a theory. So this is a theory of electrons. This is meant to be the theory of electrons moving in a given electromagnetic field, where the electromagnetic field is clamped fixed. Now, that is not quantum electrodynamics, that's the electrons moving in a fixed field. Whenever you have a theory in this situation, you see, we think of doing the path integral. The path integral is notionally defined over some space of fields up here. We think of using a Frobenius theorem or something, and doing first the integral along the fibers. That gives us something on here, that's this theory, and then to make a total physical theory, we would then integrate over all these electromagnetic fields. So we would get the total theory in the following way. We would make the space Hn, not depending on any electromagnetic field. It would consist of things, rules which to each E on N, spinor bundle, associate an element, let's call it psi N, psi in F and E. So a wave function, so to speak, a point in the Hilbert space for the space size N will be something which for each spinor bundle gives you something in the appropriate Fock space. In other words, in classical language, the wave function will depend on the electromagnetic field. And when you have an operator, when you have a coordinate N0 to N1, we want to define the UM. And at least notionally, this will be the integral of all. So this will be I usually look what things are. Just let me just write this down now. So this is meant to be something which will associate what will this, given some collection of these things, psi E, this will be on N0. We want that to take it to a collection of things, eta E1 on N1, where eta E1 will be the integral of the operator M and E acting on psi E restricted to N0. Integrated over all E's such that E restricted to N1 with E1. You see, you have the additional structures defined at each end, we want to say how to get the value of the output at P1. Well, we look at all the E's that extend P1 backwards over the manifold M. Each of those will give us a propagation, which we evaluate on the thing at the beginning of the run. You see, we will have some E0 there, some E1 here. We look at E's which interpolate between them, and we want the value there. So that's our notional vast integral. That's the process of integrating over the gauge scale.
Sorry, what does integral over empty say?
Sorry?
What does an integral over empty say? If there are no such E, that there y0 and E1 are covered.
So we start off with a cobordism. We want to define an operator for it.
Yeah, but you want to agree to your cobordism M by some field E.
Okay. So
Why did you insist?
we have a spin bundle defined at the right-hand end, and we consider all the ways of extending it to a spin bundle over the whole manifold. Conceivably, there could be none, but in that case, this would be zero, because we're integrating over nothing.
Nothing.
Well, that's very unlikely. I mean, the spin structure will usually extend to the spin structure on the cobordism. But if we did have a spin structure that couldn't be extended, then the wave function totally would vanish on that. Anyway, I just wanted to explain that schematically, because I want to use it in a different situation. According to what I know, I think I've done something wrong already. So we're going in the same order each cycle. I haven't done the three blackboard technique. So I'm only going to be interested in the most simple kind of elementary extra structures, where in the case of the additional structure, it'll be easier to much than be simply a map, a smooth map from M to some fixed auxiliary manifold. So instead of a spinner bundle, we just have this map. And then, you see, supposing we... so in this case, I'll talk about a field theory over M. Sorry, over P. So instead of considering field theories simply, we're considering field theories defined on manifolds and cobordisms over fixed manifold P. We'll call that field theory over P. Now just to get you in the right frame of mind, let's consider the example of a one-dimensional topological field theory over P. So for one-dimensional topological field theory over P, that's meant to be the same thing as a vector bundle with connection. On P. Why is it that? Well, you see, what are the objects of the cobordism category? Well, on North manifolds, equipped with a map to P, so here is P. When we have some point P naught in that, we have to associate a vector space H P naught. And when we have a one manifold with a map into P, path, in other words, we have to give an operator associated to that cobordism with its mapping to P. That will be some kind of parallel transport from this fiber to this fiber. We want everything to depend smoothly on the data, so these vector spaces should form a vector bundle, and this should be a transport operator. And why did I say a topological field theory? Well, you see, the important thing about a connection is that the parallel transport doesn't depend on how you parameterize the path. That's the topological condition, because if we took the same path parameterized two different ways, then we have two different maps of the unit integral into P, and they would be isomorphic as smooth manifolds over P. You see, so this incorporates the normal properties of connection. I started talking about these things long ago because I was interested in the case of two-dimensional conformal field theory over P, because after Wick did his work connecting the loop spaces of manifolds with elliptic cohomology, I had the idea that just as K-theory is made from these things, so elliptic cohomology should be made by using these things instead of vector bundles. So I didn't really get anywhere with it, and the subject has been pursued much more actively by Stefan Stotz and Peter Teichner. And now, well, people still haven't really succeeded in this program, but there is now a well-developed program which tries to make elliptic cohomology out of those things. But let me mention just one more thing. Let me mention the case of a p-dimensional invertible topological field theory over P. So when P equals 1, this is a complex line bundle with connection. The isomorphism classes of those things form what, depending on your culture, are like H2 DCS of P. So this is isomorphism classes or complex line bundles on P with connection. D is going to be linear Shiga assignments. So there are really two approaches to this. There's the linear theory, where you think of this as hypercohomology with values in some truncated Durand complex, and then there's the Shiga-Simons theory of differential characters. These two things are equivalent in the smooth category. The important thing about this theory in general, in fact, we could, for any P, or for any Q, we have this group which, on the one hand, is a refinement of ordinary integral cohomology. So this would assign the bundle, get the connection, and just take the first Chern class, and that's a surjection. And there's also a bundle, we have a curvature form, which is a closed Q-form on P. And any such, it's closed with interval periods. So I'll insert that. So for any closed Q-form with interval periods, we define such a bundle. So this map is also Q. So these two different teams invented the notion of something which was a integral cohomology class together with a Durand differential form representing it. So these are often called nowadays smooth or differential cohomology classes. We have them in any dimension. And one of the main facts about them is that if you have a vector bundle with connection, then in each even degree, the Chern classes of the bundle, which are integral cohomology classes, naturally lift the here. If you have a connection, you get a specific form, and so the class lifts into that. I mean, that's something you have to prove, because to give this more than just to give these two things, but not very much more. there are lots of ways of trying to define these groups and to generalize them, but what I want to say is that these things are the same thing as isomorphism classes of these are the same thing as HP plus 1. These are natural representatives for those things. And the case that we will be, I hope we'll have time to come back to later on, is the first case above the line bundles, the case where we have a 2 form, where this will be 3, where P is 2. That's something which has again lots of names, Zhao. I like to call it a string connection. So let me just explain what it is. To give one of these classes, what does it do? Well, you see, certainly among other things, there is a whenever you have a loop in P, it's the ordinary excluded loop, let's say gamma, it has to give you, because it's an invertible theory, a one-dimensional vector space. Let's call it L gamma. So it gives you a complex line bundle on the loop space. And whenever you have a cobordism with a mapping to P, it gives you some kind of operator. So, of course, if you simply took a path in the space of loops from gamma 0 to gamma 1, it would give you a map like that. So it would give you a line bundle with connection on the space, on the loop space of the manifold. But the reason why I call it a string connection is it does something better. If you take a surface with a number of inputs and outputs of any genus, so some cobordism which maps into the surface, say a sigma, then it will give you an operator at u sigma, which will go with these things as gamma 0, gamma 1, and gamma 3 from the tensor product of these lines, of the line, to the tensor product of the lines of the other end. So it's a generalization of it's a line bundle with connection on the loop space, but some additional kind of parallel transport that allows you to transport letting loops join as well. So these things represent.
Question, didn't you? Just half an hour ago, you presented the theory for the loop.
Can you speak a bit louder?
Huh?
Can you speak a bit louder?
Okay, you defined the invertible two-dimensional theory for a loop. And then you say that...
No, there's no need group here. This is just...
No, but this gives a bunch of invertible field theories when P is defined, right? Yeah.
They're not invertible. They're not
So let me just...
Yes, in spaces.
So I'm just saying, let's contemplate invertible topological field theories over P. So no group is mentioned. So this will give us, for each P minus one-dimensional manifold in the manifold line, and for each cobordism transport, with obvious compatibilities. No group.
So the circle is general P minus one-dimensional submanifold in the what you...
Yes, if we're doing it in dimension P, this will be a P minus one-dimensional manifold. So these things naturally represent integral cohomology classes together with forms in the sense of this differential cohomology.
Yeah, no. So to have this equivalence with differential cohomology, the field theory should really go down to points, right?
Yeah, right. We haven't got to that yet. We're coming to that. But yes, that's one of the... Yeah, you know too much. I hope we'll get to that. So these things in the case of P equals 2 are often called B fields on P. things is exactly that. Two-dimensional invertible topological field theory of P.
It's beefy.
So it's one of these things, big connectors. And they have their main invariant as an integral three-dimensional topological function. Because, so in particular, see, for a closed manifold, they give us a number. Cheek assignments define differential characters in dimension 3 as circle value functions on closed manifolds of one lower dimension in the target, and satisfying certain conditions, and those conditions are built into this structure. Right. Now, this was a long digression, so I hope you haven't forgotten what it was meant to be about. I was meant to give you this trivial argument for the theory associated to a Frobenius algebra, which wasn't one-dimensional. I was going to tell you how to define the direct sum, so to speak, of cohomology theories. So, suppose we have some quantum field theories of a certain dimension d, it doesn't matter what, a finite number indexed by a set p, which is a finite set. So we're now going to specialize this whole structure down to a finite set p. We have a finite number of theories. Let's define a new theory defined on manifolds over P. So we have a space whenever we have a map like that. This is a smooth map because it's a finite set. We have to define something H N and F, and we will simply define it. We'll simply do the tensor product or alpha or F alpha applied to F inverse of alpha. That's part of it. You see, so the different pieces are different components of alpha are indexed with this tensor together. Well, now we can integrate over all these fields. So with sum, we'll define a total theory, which will just be the direct sum of the over all maps in P. Of H and F. And the fact that there is R theory is trivial. I mean, in the case where P is a finite set, this is just trivial combinatorics. So there's nothing really to check. But you see this gives you a new theory which you can call the direct sum of that finite set of theories. And if we do that for a number of one-dimensional Frobenius algebras, we get a general Frobenius algebra. Okay, now we want to change yarn again. Maybe possible the order of these blackboards. I think you have to graph German between blackboards. And so now we have to start having these. So there's an obvious inadequacy in the definition of a quantum field theory that I have been working with. So what is this inadequacy? Well, it's that the definition is not sufficiently local. What does that mean? You see, roughly, we were interested in studying some space-time manifold M. And I have given you some rules which say that if we cut this into two along a membrane, then if we know stuff for M1 and M2, we know how to put it together and get something for M. But that isn't so good. I mean, that isn't all we need to do. for example, supposing you had a triangulated surface, you divide it up into little triangles. Well, each triangle has Euler number 1. Now, I said Euler number was additive, but there's this intersection term. So you can't get the Euler number of a surface by adding up 1 for each triangle in the triangulation. It's a bit more complicated than that. In other words, you have to say what happens when you have corners and things like that, if you want to be able to make a manifold up out of small pieces. Well, why do we care about locality? Well, because there might be lots of reasons, but the reason I care about locality, mostly, is because one wants to define a moduli space of these theories, and in order to define a moduli space, you want to know what an infinitesimal deformation of a theory is. Now, an infinitesimal deformation of a theory, any physicist will tell you, is given by some field in the theory. You see, we have some operator associated to M. If we know how the operator changes just in a little bit of a region, you see, if we can describe the deformation of the theory separately in each little tiny bit, then that means in every tiny little bit we have to give a field, essentially, because that's something in the space associated with the boundary of that little bit. That will be the first step towards having the tangent space to the space of deformation. So this is why I care about locality. Why am I interested in making a moduli space of theories? Well, as I said, I hope in the first lecture, one of the backgrounds to this whole point of view is one would like to say that two-dimensional conformal field theories somehow roughly correspond to Riemannian manifolds, in fact, Ricci flat. So this is a very schematic and absolutely not precisely proved statement with some additional structure with a B field and actually a uniform field. The Dirac field is a sort of extra volume element on the manifold as well as the volume element coming from the Riemannian structure. So it's sort of a pair. The thing has two different volumes now. Don't worry about that. So the B field is what I told you a second ago. Now this is a very rough correspondence. This is meant to be, when we take such a manifold P, then we can consider the idea of integrating the theory, so-called sigma model of P. The theory is the theory of all the field space phi M is all the maps from M into P. And you see the action is just the usual integral over M d phi. Phi is a field. Star d phi. That's a two-form, because this is meant to be a surface. The two-dimensional theory. These are two one-forms. That makes good sense. And we can add on the B field. Remember, if we had a B field here, it pulls back to whenever we have a surface in there, it will give us a number. Which we, speaking, I should say, e to the is is e to the I of this times the B field. So I was writing the B field not figuratively, not actually. Okay. Well, now, what evidence might there be for this even notion? Well, the evidence such as it is that for some P's at least, you can construct this sigma model. Certainly, for instance, if P is a torus, you can undoubtedly construct this very explicitly. You can then ask, what are the infinitesimal deformations? Well, if you have a description of deformations in terms of local fields, it's a simple task to check which deformations will deform it to a conformal theory. And if you do that, you'll find that the tangent space of the space of theories is precisely the tangent space for this well understood moduli space of these Ricci flat manifolds with additional structure. Now there's an even wilder idea which the most intensive works have done by Zamanotchikov, I suppose. We might try to relax the conformal conditions, take that away, and that's meant to correspond to taking away the Ricci flat condition. Now if we don't have Ricci flat in there, then of course on this side we have the Ricci flow, of which the Ricci flat things are the fixed points. That's meant to correspond, if you believe this correspondence, to a wonderful flow on this side, which is the renormalization of group flow, which in the language I'm using is very simple to describe. You see, if you have Riemannian manifolds on which your theory is defined, you can simply rescale the metric, just multiply all the metrics by a number. That will take any theory to a new theory, and that's the renormalization of group flow on this side. So, infinitesimally in perturbation theory, Zamanotchikov sort of proved that this Ricci flow in a sort of physical level of rigor corresponds to this. And it would be very nice to make that into a really proper mathematical theorem. I'm not claiming to be able to do that, but that's the direction in which I'm going, which makes me want to understand what an infinitesimal deformation of the theory is. I've only got another 5 minutes, so I'm going to tell you one more thing, I think.
I thought that there was something by Zamalotchikov that some function along some flow of degrees.
Right.
So what is it in your language?
So I haven't got that far, but the two-dimensional conformal theory has a number associated with it called the central charge. And what Zamalotchikov proved was that this is monotonic along the trajectories of this flow. That was called Zamalotchikov's C theorem. But not very helpful if I don't tell you what the central charge is in the plane. So let me just quickly, as I'm getting so late, step away from this. So we'd like to rectify this problem of put in some more locality. Now, the interesting thing is that this has become a very big industry, and I'm very old and I'm not really into higher categories, so I'm going to give you a very old-fashioned take on it. Well, anyway, just for the moment, I'm going to begin with a simple example. So, I mentioned the Euler number. Let's think about the signature of the form number. That's really all I have time to do now. So the signature of the quadratic form on the middle homology. Now, Novikov proved a very long time ago that this was additive in the sense that if you cut a four-manifold into two pieces along a three-manifold, then a four-manifold with boundary has a signature. The quadratic form is not non-degenerate, but it still has a signature, and the signature adds. However, everyone knows that that has the same problem with the Euler number, and the classic example is to take the complex projective plane and think of it as three homogeneous coordinates given by three homogeneous coordinates and divided into three regions by where each of the one of the coordinates is biggest. So we divide this into three solid balls, D4, 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 each of them being where one of the coordinates is biggest in absolute value. So something like that is a three-sphere with a corner here, and this thing in the middle is of codimension 2. This is an ordinary two-dimensional torus, S1 plus S1. Now here you see the problem of the signature, because this thing has signature 1, and this is completely symmetrical. The disk has signature 0 presumably, and 0 plus 0 plus 0 is not equal to 1. So there's some correction which has to somehow to do with that triple thing in the middle, the fact that we have something in codimension 2 where things bifurcate. And this phenomenon was first understood and explained quantitatively by Cherry Wall, who observed that in general we have some surface here. Suppose we have a surface. We look at its real homology in dimension 1. That's the finite dimensional symplectic vector space that has a skew form coming from the product. And so let's imagine this let's imagine this in the general case, where we have M0, M1, M2, and M3, and some surface in the middle. So here we have some three manifolds with boundary. Each of them has boundary sigma. When you have a three manifold with a surface boundary, the image of its cohomology in this gives you a Lagrangian subspace in this cohomology. So each Mi defines a point in the Lagrangian graphs the maximum half-dimension isotopic subspace is. Well, this is something, of course, of the space which is fundamental to the integers. So let's just draw that Lagrangian thing as a circle. Each of the three m's gives you a point in it. And what Wall realized was that each of they correspond to the m's. But each of the four manifolds, these were the, these were, let's call it N1, 2, and so on, N9, so we have 3 points in that Lagrangian subspace. And each of the m's defines a, you see this, what we want to say is that associated to these two things which are stuck together to form a closed three manifold, we can consider the groupoid, the fundamental groupoid, in the fundamental groupoid, the paths which go from there to there. That's an affine copy of the integers. Right? We have a space whose fundamental group is the integers. We're looking at the paths from somewhere to somewhere up to homotopy. That's an torso, an affine space for the integers. And what Wall observed was that there is a element of the groupoid associated to each of these manifolds. And the correction, so together they give you a closed path in the Lagrangian Grassmannian, and Wall observed that the number by which you have to correct is the homotopic class of that path. Well, now let's fit this into our field theory perspective. I think we did touch that. I'll just take very, very quickly and then I'll stop. I'm really sorry for overtime on this. We're writing this all additively, so I'm not usually.
Precise zero or is this a precise zero or
That's a precise term of order. Hope so.
Can you formulate this again?
why don't I try and say it in the field theory way? I mean, in this particular situation, if we have three manifolds with a surface boundary, we get 3 points in this Lagrangian submanifold. So the theorem is that each of the four manifolds defines an element of the fundamental groupoid of this space, consisting of a path going from that point to that point. So it has a kind of signature which is in there. And the correction to the signature formula is this one. But let me try and say it in a slightly different perspective. So I want to tell you a formalism in which to do this. So we want to talk about four-dimensional topological field theory. So to close three manifold, it's going to be written additively. So this is going to give us, to a closed four manifold, we're going to give some number m, which is an integer. So this is a more additive version of what we usually say. Now to a three-dimensional closed thing, I want to associate a z torso. So the principal homogeneous space for the integers, so an affine copy of z in that fundamental group. To a closed surface, we want to associate a category, namely the fundamental groupoid, which are right now is of the category, which in this case will be that fundamental groupoid. It will be a category in which the morphisms from any object to any other object are the z torso. Now, we want the following situation. When we have a cobordism like this, n, so a non-closed three-manifold, we want this to give us a functor from this to this. And when we have a closed, when we have a non-closed three-manifold, we want to say that U(m) will be in. Sorry. I've really gone too long. I think I'd really better leave this and say it properly next time. Really sorry too long. I've gone so long over time, but I think I'd sooner say it properly next time rather